So I think it's a pretty cool example of mean value theorem and how it might come into play, um, in the real world and in all of our experience. So it says, on a certain highway, a car passes one checkpoint at 11:17 a.m. and a second checkpoint at 11:45 a.m. So imagine, you're driving across the country maybe, and you're out, um, in this wide open spaces in the plains or the desert someplace, and there are just these checkpoints, and you don't necessarily have to stop at the checkpoints, but you go through them, and the checkpoint notes maybe your license plate and what time you drove through. Okay, so this car goes through these two checkpoints, one at 11:17 and a second at 11:45. The checkpoints are 41 miles apart on this wide open stretch of highway. Could the driver be ticketed for speeding over the 65-mile-per-hour limit based on this information alone? Now, when you first read this, it doesn't seem like a calculus question, and the truth is we can get to an answer without any calculus. And we're going to do that, but then we're going to look back and like, how does this connect to the mean value theorem? Okay, so let's just try it out. All we know is how far apart these checkpoints are and how much time it took for the driver to get from one to the other. So here's what we're going to do. We're going to find the driver's average speed. Okay, the driver's average speed is the number of miles that were driven or covered divided by how many hours it took. Right, let's do this in miles per hour. So how do we do that? Well, he covered 41 miles. And if we want the number of hours it took, well, 45 minus 17, I just took the minutes, 45, and okay, that's how many minutes it took. So then I got to divide that by 60 so that I get the number of hours. Okay. So what is it, like 28 minutes or so? But then I divide the 28 minutes by 60 to get the number of hours. All right, if we compute that, what's the driver's average speed in miles per hour? And okay, yeah, it turns out his average or her average speed, 87.9 miles per hour. So, could the driver be ticketed for speeding over the limit of 65 miles an hour based on this information alone? Yes. Yes, they could be ticketed. Nobody has to actually be out there on the highway and hit them with a radar gun going 87.9 miles per hour. If they went 41 miles in only, 28 minutes, then they were averaging 87.9 miles an hour. They definitely were speeding. Okay, how does this tie in to the mean value theorem? Here's what's going on. Show you in a graph. So imagine we've got time and we've got the number of miles that they cover. So we'll say at 11:17 they had gone 0 miles. Obviously they're driving down the highway. They've already, all right, but okay, we'll just say that's time 0. 0 miles. 28 minutes later, they're 41 miles down the road. We have no idea how exactly these 2 points are connected. Maybe they were driving the same speed on cruise control or whatever, the whole way. If they were driving exactly the same speed, it would be a straight line. But that's probably not the case. They probably sped up at some points, slowed down a little bit at other points. Who knows? Maybe they stopped completely for a few minutes in the middle. We don't know. So we're just going to draw this, we do know that it will be continuous. Even if they stopped completely, that would just mean the line goes horizontal for a time because they're not gaining any more miles, right? So here I've got them going quite fast here, and then they really, really, really slow down a lot. You know, there might have been a small town in the middle. We don't know. Might have stopped on the side of the road for whatever reason. And then they were speeding back up again, and after 28 minutes, they've covered 41 miles. If we can calculate the slope of that line connecting the endpoints, then we know that at least one moment, and here there would be two, the slope of the tangent line would be parallel to this line down the middle. Well, if the slope of this line is 87.9, then at least at two, or at least at one moment, you know, because it might have gone up or might have kind of swooped, at least one moment during that trip, they were going 87.9 miles per hour. And calculus, with the power of calculus and the mean value theorem, we can write them a ticket. Now, the truth is, they would only, that would have been their maximum speed only if they drove that entire distance at that same speed continuously. But it's more likely that they sped up a little bit and slowed down at other points. So actually, they were probably driving even faster than this at some other periods. Like here, you know, the slope is even faster. So they were going well over 100 right here, and then they started to slow up, and then they started going again. But, you know, we can say without any doubt that they were going this fast at least one point. So there you go. Okay. Another question that you might see might look a little something like this. For f of x equals tangent x, is there a value of c on 0 to pi that satisfies Rolle's theorem? If so, find it. If not, explain. Okay, let's check this out. Now, the way I began was just to look at, now we're back to Rolle's theorem here. I was just going to look at the hypotheses of Rolle's theorem, which is not quite the way it's phrased. It's a little bit deceptive. It just says, is there a value that satisfies Rolle's theorem? So it's almost like, hey, just go find the C, you know. But wait a second. Let's make sure that the hypotheses are met first. So for one, is that function continuous on the interval 0 to pi? You think, all right, well, we're talking about tangent x. Hey, is tangent x continuous across 0 to pi? Actually, no. There's a vertical asymptote at pi over 2. And so, if you're not even satisfying Rolle's theorem, then there's no guarantee that you're going to meet the conclusion of the theorem, right, if you can't even meet the hypothesis. So a C value, here's my explanation. A C value satisfying Rolle's theorem need not exist because f of x is not continuous on the interval. And we'd probably just circle that and say we're done. But what if we look further? Like, okay, so maybe we don't meet the hypotheses, but does that mean there's not a C value? It's not guaranteed, but it need not exist, but it still might. So, you know, let's just explore this a little bit further. What if we, you know, took a derivative and set it equal to 0, right? That's how we find the C value in Rolle's theorem. Like, okay, I'll just show you all my steps here. Actually, we looked at the endpoints here. My mistake. So f of 0, right? Our interval is 0 to pi. So let's plug both of those endpoints in, and we do get the same thing. These two do equal one another. So at least that part's true, even if it's not continuous, which would mean not differentiable either. If we take the derivative of tangent, it's secant squared. But if we try to set secant squared equal to 0 and solve, well, we're not going to get very far. secant squared won't ever equal 0. And well, why is that? Well, because secant is 1 over cosine squared x. And like, well, what value of x would you put in to get 0? And well, right, the cosine of 0 is 1. So cosine 0 would be 1 over 1. There's nothing you can do to plug in, right? This just doesn't happen. Neither of these work. So it need not exist, and it doesn't exist. So one thing to look out for, some of these problems are going to try and kind of trick you, or you might even, just in wanting to get to an answer quickly, you might say, okay, perfect, I'll set the derivative equal to 0 and solve. And it's like you just fly right past the fact that it has to meet the 3 hypotheses for Rolle's theorem, or the 2 hypotheses for the mean value theorem. And you kind of left like scratching your head. Why can't I get an answer? Well, maybe it never satisfied it in the first place. Okay, that is 4.2. Good luck in the homework.